Hello viewers, Wagadaruna taking you through the story for A-level applied mathematics. And this video we are going to go through the topic of probability theory. So this video is suitable for students in both Senior 5 and Senior 6 offering principal mathematics as part of their combination. So before we start, let's first look at the course outline and our progress so far on this platform. Now, math paper 2 is divided into 3 parts. The first part is mechanics, then the second part, the first part is mechanics, and mechanics is further divided into 3 parts. So the first part of mechanics is kinematics, where one comes in section A and one in section B, and these are the topics. The second part of mechanics is called dynamics, where one comes in section A, one in section B, and these are the topics. The third part of mechanics is called statics, where one comes in section A and one in section B, and these are the topics. So in total, 3 questions come in section A and 3 in section B under mechanics. Then the second part is statistics and probability, where 3 come in section A and 3 in section B, and these are the topics. And the last part is numerical methods, where 2 come in section A and 2 in section B, and these are the topics. So far numerical methods is entirely complete, and in this video we shall complete the part of statistics and probability with these 2 videos. Now, permutation and combination, we covered it in pure mathematics, but for this, the one for applied mathematics is a little different in that it involves that part of getting probabilities. The one for pure mathematics was for number of ways of arranging or number of ways of combinations, but here we are interested in getting probability using permutation and combinations. So after this video, then the remaining part will be on mechanics. So after this video, you must prepare your minds for mechanics, because that will be the remaining part in applied math. So probability is defined as the extent to which an event is likely to occur, or you can say is the measure of how likely events are to happen. Now, probability in O-level, you covered probability, and there are some terms which you learned from your O-level. So let's first list them down. One is the term of outcome, such as that in a trial or experiment, the things that happen are what we call outcomes. So this term you covered it in your O-level. So for example, if a 6-sided dice is rolled, the numbers 1, 2, 3, 4, 5, and 6 are what we call the outcomes. Then another term you learned from O-level is what we call the sample space. So a set of all possible outcomes is what we call the sample space. Then another term you learned in O-level is what we call events. So events are groups of one or more outcomes. So a possible event for a dice rolled is that you roll an odd number. An odd number can be 1 or 3 or 5. Another possible event is that you will roll an even number. So 2, 4, or 6 is what we call is an even number. So this is what we call the event. So event of rolling an odd number or event of rolling an even number. If any outcome corresponding to an event happens, then we can say that an event has happened. So basically that's what an event is. So next we shall come and say that when all the possible outcomes are equally likely, you can work out the probability of an event using the formula this. So in your O-level, the events were all the outcomes were equally likely. So all the outcomes you covered in your O-level were equally likely. Now here we shall add in some other things. So the probability which we learned is that probability of an event is equal to the number of times an event occurs over the sample over the sample space. So this is the probability of an event, number of outcomes where an event happens, and this is the total number of possible outcomes, what we call the sample space. The another thing we need to remember is that if a trial consists of two separate activities, then a good way to draw a sample space is to draw a sample space as a table with the outcomes for one activity along the top and the outcomes of the other activity down the left hand side. So that means that you draw a table whereby you put here the first outcome and here the second outcome, and these will be the combinations. For example, here it can be a head, and here it can be it can be a coin, outcomes of a coin, and the outcomes of a dice, as we shall see in the examples. So what we are reading is what we recall from our O-level. So remember that the probability of an event has to be between 0 and 1. I think you remember that. So probability can never be negative and can never be more than 1. When the probability is 0, it implies that the event is impossible. It can never happen. And when the probability is 1, it implies the event is certain to happen. There is no doubt that it will happen. So that has been a review from our O-level. So now we shall start our topic. So we shall start with interaction with set theory. So probability theory and set theory are interrelated, and most of the probability theory laws are obtained using set theory. So here we shall consider two events, A and B, and therefore shall draw our Venn diagram having those two events. So first we shall have probability of A. Now probability of A, it takes entirely those ones, the whole of this which is shaded. Then probability of B, it takes that, the whole of that. Then probability of A intersection B, probability of A intersection B, it takes that. Then probability of A intersection B complement. So this is what we used to call A only in our O-level. So A intersection B complement, it will be that. Then probability of A complement intersection B, we shall shade that. Then probability of A complement intersection B complement, if I am to shade it, to be that, what is outside A and B. Then sample space, like I told you, total probability is always equal to 1. That is why you put here 1. When you add up everything here in this Venn diagram, you must get 1 as the total probability. Now from here we shall come up with some probability theory laws using this set theory. Let's look at those laws. So from the above set, the following identities can be obtained. One shall realize that probability of A is equal to probability of A intersection B plus probability of A intersection B complement. Let's first look at that. So if I want to get probability of A, remember probability of A is the whole of this, and to get it to be equal to probability of A intersection B complement plus probability of A intersection B. That is why you are seeing it here. Then another identity you can get from set theory is that probability of A complement is equal to probability of A complement intersection B plus probability of A complement intersection B complement. Now here there is something I want you to realize. One is that what is here remains unchanged. Then you can see here this A was unchanged because it was what is here, but B changed, the other event changed. Then when it came to A complement remained unchanged, but the other event changed. So that is the only trick you can use to remember these identities. Then probability of A plus probability of A complement is equal to 1. I think this is usual because we know it and we use it frequently in our O-level. Then the second identity is on event B. So still, like I said, what is here will never change, but the other event changes. That is the only way you can easily memorize. Therefore, probability of B complement will be still B complement will not change, but for A it will change. Then also probability of B plus probability of B complement must be equal to 1. So next we shall go to identity 3. So identity 3, if you look at this, I want to get an identity which gives me the probability of A union B. So A union B is the whole of this. Therefore I have to add up all these three probabilities, this plus this plus this. And that's what I have done here. That's what I've done there. Therefore, there is something we have already realized. We already saw in identity 1 that probability of A is equal to probability of this plus probability of this. So when I make this one the subject, I'll come up with probability of A minus probability of A intersection B. Similarly, in identity 2 we saw this. So when I make A complement intersection B the subject, I'll come up with probability of B minus probability of A intersection B. I think remember that from identity 2. Now what I'm going to do, I'm going to substitute this one here to substitute for that here, and also substitute for this here. Let's do that. Okay. The next is to collect like terms. You realize that this one and this one can cancel. So I'm going to remain with this probability of A, this probability of B, and this minus probability of A intersection B. So this is the identity we shall use more frequently. So each time they ask for probability of A union B, remember that will be equal to probability of A plus probability of B minus probability of A intersection B. So this is what we call the union of two events A and B. And similarly, we can also play about with it by adding some complements. So if this is B complement, means that you maintain the B complement. And if there is A complement, means that you also maintain the A complement. And if there are complements on both, means you still maintain the complements on both. So now we shall go to what we call the contingency table. Now this one is similar to the one of Venn diagram. It summarizes the identities we got from set theory. So you can either choose to memorize this contingency table or to memorize the set theory, because they both do the same thing. So this is a table of probabilities of intersection of sets and their complements. So if we consider two events A and B, we can draw our contingency table in this form. First, the first event is put here and its complement. Then here we shall just write the word sum, which is what it means. Then second is put here the second event plus its complement. Then here we shall write the word sum, which is what it means. Now here it means that we are going to combine A and B, so we shall put the A intersection B. Then here we are going to combine A complement and B, therefore we shall write A complement intersection B. And here we're going to write, we shall combine A with B complement and write A intersection B complement. And here we combine A complement and B complement to write A complement intersection B complement. Then now here we shall get this and make the probability. and here I shall get this and make it a probability, and here I shall get this and make it a probability, get this and make it a probability, and here I shall put 1. So how does this contingency table work? So this contingency table will consider sums horizontally and vertically. So let's first consider sums horizontally. So horizontally means this plus this gives you this, and this plus this gives you this, and this plus this gives you that. Therefore, you shall come up with those sets of identities. That is horizontally. Then vertically, this plus this is equal to this, this plus this is equal to this, and this plus this is equal to this, and that will give you those identities. So that is how a contingency table is used. But still, if you don't want to use this contingency table or set theory, you can remember that what is here is maintained and the other event changes. What is here is maintained and the other event changes, and also what is here is maintained and other event changes. What is here is maintained and what other event changes. So with that knowledge, let's go through these questions. Question 1 says, for events A and B, probability of A is equal to 0.4, probability of B is equal to 0.5, and probability of A intersection B is 0.15. Part A, draw a Venn diagram to represent the events A and B. Then part B, find Roman 1, this, and that. So shall first begin with drawing our Venn diagram. So first we apply the total probability is equal to 1. The next probability of A is equal to 0.4, it was given. Probability of B is 0.5, it was given. Then probability of A intersection B is 0.15, it was given. So here they didn't give us what to put here, but remember that this one covers this and this. Therefore, that means that this minus this gives you what is here. That is why we are subtracting. Then when I subtract, I'll come up with 0.25 as the probability for A only, or we can call it A intersection B complement. Then for B only, it will be this minus this to give you this part. And now as you can show it becomes 0.35. Then what is outside, we don't know it yet. Now shall you answer the questions. So for Roman 1, they want A intersection B complement. A intersection B complement means A only, which is 0.25. Then for Roman 2, they want probability of A complement intersection B, which is B only. Therefore, B only is 0.35, which is that. Then Roman 3, they want probability of A union B. Now A union B, it means we're going to add up this plus this plus this. So when I add them up, I'll come up with that. So this plus this, I can choose a shortcut by writing this, because when I add, I'll come up with this. So that's what I've done here. Shortcut is this probability plus this. If not, I'll have to write this plus that. Then Roman 4, probability of A complement intersection B complement. So what is outside the set? This value of X is what they want. So shall remember that this one is the same as 1 minus this union. So the whole of this, remember this 1 is equal to the whole of this plus this. Therefore, when I want to make this the subject, I will say 1 minus the whole of this. This is what I've done here. Therefore, I come and substitute for A union B to come up with this as the value of X, or the value of A complement intersection B complement. That was question 1. Now question 2 says, if probability of A complement is 0.36, probability of B is 0.44, and probability of A intersection B is 0.27. Find this, and that. So we shall start with Roman 1, probability of B complement. Remember, probability of B plus probability of B complement is equal to 1. Therefore, when I make B complement the subject, I'll come up with 1 minus probability of B. And the good thing, probability of B is given here. So I'll end up with 0.56 as probability of B complement. Then Roman 2, probability of A union B. So remember the rule that A union B is equal to probability of A plus probability of B minus, so this is a minus probability of A intersection B. Now probability of A can be got from this to be 1 minus probability of A complement. That is why we are seeing here 1 minus 0.36 to give you probability of A. Then probability of B is already given, and A intersection B is also given. So in the end, you shall come up with this when you use the calculator. Then Roman 3, they want probability of A intersection B complement. Now from Contingency Table, you realize that A intersection B complement is equal to probability of A minus probability of A intersection B. Like I told you, what is here will not change. So I'm going to substitute probability of A is this, probability of A intersection B is that, therefore I'll come up with this as the answer. Then next they wanted probability of A union B complement. So A union B complement, I'll still expand probability of A plus probability of A complement, sorry, probability of B complement minus probability of A intersection B complement. Now I already know the probability of A is this. Probability of B complement, I already got it in Roman 1. Then probability of A intersection B complement, I got it in Roman 3. So in the end, I'll come up with 0.83. That was question 2. Now we shall go to question 3. Question 3 says if probability of X union U union Y is equal to 0.77, probability of X is 0.43, probability of Y is 0.56. Find this, and that. So it's the same procedure, so you can either choose to pause the video and first work it out, then you can check your progress. So in Roman 1, Y complements to the same procedure, 1 minus probability of Y, which gives you 0.44. Then for Roman 2, X intersection Y. So first of all, the good thing in the question, we are given probability of X union Y. So when I expand this, I'll come up with probability of X plus probability of Y minus probability of X intersection Y. So I'm going to substitute for this union and also for this probability of X and for this probability of Y. I remain with this as the only unknown. So I have to look for a way of making it the subject. And the answer will be 0.22. Then Roman 3, probability of X complement intersection Y complement. So still this is the same as 1 minus probability of X union Y. We already saw that in question 2. Therefore, when I substitute union, I'll come up with this as the answer. Then Roman 4, X complement union Y complement. So X complement union Y complement is equal to 1 minus X intersection Y. I think remember that when we are shading, we shaded everything else but left the intersection unshaded for this. Therefore it means that you have to say 1 minus this intersection. When I substitute, I'll come up with 0.78 as my answer. Then question 4 says if probability of C complement union D is equal to 0.65, probability of C is 0.53, and probability of D is equal to 0.44, find this, and that. So still you can pause the video and first work it out. So for Roman 1, they want probability of C complement intersection D. But the good thing, we know this probability of C, so probability of C complement will be 1 minus probability of C, which gives you 0.47. but that's not what they want. Remember, they want this. Therefore, I'll come here and say that probability of C complement union D, when I expand, it will be probability of C complement plus probability of D minus probability of C complement intersection D. Therefore, I'll come and substitute for this union, substitute for C complement, and substitute for D. I'll only have this as the only unknown. Therefore, I have to look for a way of making it the subject, and the answer will be 0.26. Then for Roman 2, they want probability of C complement intersection D complement. From Contingency Table, I realize that this is equal to this minus this. I can either, like I told you, I can either use set theory or Contingency Table, or I can remember that what is here does not change. Any of the three is okay. So this is this and this is this. Therefore, when I subtract, I'll come up with 0.21. Then for Roman 3, probability of C complement union D complement. I'll still come and expand it using the union. So this is C complement plus probability of D complement minus the intersection. Therefore, I come and substitute for each and come up with 0.82 as the answer. Then Roman 4, they want C intersection D. So remember that I already know that this is equal to 1 minus this. Therefore, I come and substitute for this and look for making this the subject, and in the end I'll come up with 0.18. So that was interaction with set theory. Now shall go to the laws of probability theory. So these laws simply help us to calculate required probabilities. So we shall consider a random experiment whose sample space is S, and we shall let A and B to be any two events, and here we shall use this symbol and this symbol to denote complements. So this is A complement and this is B complement. The first law is what we call De Morgan's law. It says that for any two events A and B, probability of A complement union B complement is equal to probability of brackets A intersection B, everything we put it under a complement. Now realize that here the complement is on each event, and here the complement is on the entire event, entire events of A and B. Then another thing you realize is that here the sign was union and here the sign is intersection, so the sign changes and the complement goes outside the bracket. Similarly here, this sign will change, it was intersection, it becomes union, and the complement goes outside the bracket. That's what you need to remember under De Morgan's law. Like we told you, they help us to easily calculate required probabilities, and we shall see how. The next is commutative laws. Now it says that for any two events A and B, probability of A intersection B is the same as probability of B intersection A. So when you interchange this, as long as it's intersection, it is the same. Also, as long as it is union, it remains the same. That is commutative law. Then in idempotent laws, it says that for any two events A and B, probability of A intersection A is equal to probability of A. So sometimes the examiner can trick you and say, find the probability of A intersection A. Then you may wonder what to do, but always remember that when they say A intersection A, it means probability of A. And when they say A union A, it means probability of A. When they say B intersection B, it means probability of B. And when they say B union B, it means probability of B. So that's what idempotent law means. Then law number 4 is what we call the universal law. So remember we said S is the sample space, so an event union the sample space gives you that sample space, which is equal to 1. while an event intersection in sample space gives you that very event. That is the difference. Here for union it is the sample space, for intersection it is the event. So those are the 4 laws which are very useful in a level. So now shall go to what we call probability situations. So what you have seen previously, we have been using union and intersection, but sometimes they can give you a probability in words. Instead of saying find probability of A intersection B, they can give you in words and they write it like this, or A intersection B complement, they write this. So it is you to remember that when they write this, it means this. So that's what this slide is about. So we shall start with what we call the AND situation. So there are 2 situations. We have the AND situation, which deals with intersections, and what we call the OR situation, which deals with the union. So shall look at both of them before we go to worked examples. So this arises under 2 circumstances. One is when we are interested in the joint occurrence of events. Then 2, when we are considering a sequence of events. Therefore, from probability theory laws, AND means intersection. That's what I've told you. So when you see this word AND, you should remember that it means intersection. What does that mean? It implies that if they say probability that both events A and B occur, you should write it as probability of A intersection B. And the probability that only event A occurs, you should write it as probability of A intersection B complement. And the probability that only event B occurs, you should write it as A complement intersection B. Now what you see in brackets, it means it is optional. So a question can say, I can choose to say find the probability that only event A occurs, and I stop there. Or I can choose to say find the probability that only event A occurs and event B does not occur. So it is up to the examiner to choose whether to complete the statement or to only write it up to here. But it all means the same. Then when I say probability that neither event A nor event B occurs, it means A complement intersection B complement. So that has been the AND situation. Now we shall go to the second situation, which we call the OR situation. So this is a situation in which we are interested in the occurrence of either 1 or 2 or 3 or all the events in the question. This actually represents the occurrence of at least one of the events. So remember, the AND means joint occurrence, but here it is at least one. Therefore, if I have 2 events A and B, the probability that either A or B or even both occur is noted as probability of A union B. So when I can choose to write it in words, and I say find the probability that either A or B or both occur. So it means, always remember that means union as long as you see this word O. And like we already saw, union is expanded in this form. But there is also another common term which appears in A-level and is very common. It says the probability that exactly one of them occurs. So the probability that either A only or B only will be denoted by A union B minus A intersection B. Remember, A union B, the intersection is also included, but here they said A only or B only. Therefore it means that you have to eliminate the intersection by subtraction. And when I expand, I already know that A union B is this, so when I substitute it here, I'll come up with this, with a 2 here, because they will be this and also this to give you that 2. So this is very common, and we shall also see it in the worked examples. So question 1 says 2 ordinary die are thrown. Find the probability that the sum of the scores obtained is Roman 1, part A, a multiple of 5, part B greater than 9, part C multiple of 5 and greater than 9, and part D multiple of 5 or greater than 9. So note this word and the word or. So like we said, we shall generate the sample space by tabulation. So we shall come and draw our table. One event, we shall put one event here, and also we shall put another event here, and its possible outcomes. The next, remember the question is on the sum. It talks about sum. Let's just look at the question. The question talks about sums of the score. Therefore, we have to add. It means that when I add 1 plus 1, I'll come up with this. Then 2 plus 1, I'll come up with 3. 3 plus 1, 4 plus 1, 5 plus 1, 6 plus 1, and that column will be done. The next column, 1 plus 2, 2 plus 2, 3 plus 2, 4 plus 2, 5 plus 2, 6 plus 2. So when I do that for all the columns, for this column I'll come up with 4, 5, 6, 7, 8, 9. Then for this other column I'll come up with 5, 6, 7, 8, 9, 10. Then for this other column I'll come up with 6, 7, 8, 9, 10, 11. And for this other column I'll come up with 7, 8, 9, 10, 11, 12. So those are my sums. Now shall we say let S denote the sample space. That implies that S is equal to 36. Sample space, for example, this is the whole of this. If I count all of them, I'll come up with 36 because this is 6, this is 6. So 6 times 6 gives you 36 outcomes. And shall let A to denote multiple of 5 and B to denote greater than 9, because that's what the question is about. Then when you go to question A, part A said probably that the sum is a multiple of 5. So it means that in these sums we shall look for multiples of 5, and all those are multiples of 5. So we shall count them 1, 2, 3, 4, 5, 6, 7. And like we realized that probability is equal to probability of an event is equal to event over sample space. Therefore, we shall come here and write here 7 over the sample space, which is 36, and that's what they wanted. Then for part B, probably they want the sum to be greater than 9. So you come here and look for sums which are greater than 9. And those are 1, 2, 3, 4, 5, 6. Therefore the number of event is 6, therefore the probability will be 6 over 36. You can choose stop here or you complete by reducing. Any is okay. Then now shall go to part C. So for part C they want multiple of 5 and greater than 9. That means that they want a joint occurrence. So both multiples of greater than 9 and also multiples of 5, you realize that the intersection will be, there is this 10 is both a multiple of 5 and greater than 9, multiple of 5 greater than 9, multiple of 5 and greater than 9. So they are only 3. Therefore you come here and say that it will be 3 over 36. Then next is multiple of 5 or greater than 9. So that means that you take everything that is shaded. Therefore we shall come and count but without repetition. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Therefore we shall come here and write that the required probability will be 10 over 36. So this has been got by counting, or you can choose to say probability of A union B is equal to probability of A plus probability of A plus probability of B minus probability of A intersection B. So you will still get the same answer. So that has been question 1. Now we shall go to question 2. Question 2 says two events M and N are such that probability of M is equal to 0.7, probability of M intersection N is equal to 0.45, and probability of M complement intersection N complement is equal to 0.18. Find probability of N complement. And part B, probability of M or N but not both M and N. So let's start with part A. So for part A, we shall remember this from our contingency table. Like I said, if you don't want to use contingency table, you should remember that what is here will never change, but the rest, the other event changes. So next is to substitute. So the probability of M is that, and the intersection is that. So I'll come up with 0.25 as this probability of M intersection N complement. Then now that I've got that, I can easily get my N complement. Still from contingency table, N complement means that N does not change. N complement does not change, but this other one changes. The next is substitute. This is here and this is that. And when I add that, come up with 0.43. And that has been part A. Now part B, they said M or N but not both. That means that this one union minus the intersection, because they said but not both. And remember, intersection also includes union includes an intersection. So this means this word but not both means that you have to eliminate the intersection. Therefore, I come and say that this one means probability of A union N, M union N minus the intersection. And when I expand this, I'll come up with this. I think you already saw that under the O situation. The next is substitute for M, for N, and for the intersection. And I'll come up with 0.37 as the answer. Then question 3 says the probability that events A and B occur are a third and a quarter respectively. So this a third is for event A and a quarter is for event B. Given that the probability that only one of them occurs is 5 over 12. Note that word, only one of them. Find the probability that both events occur and none of them occurs. So first of all, we know that probability of A is a third and probability of B is a quarter. Then probability that only one of them occurs is 5 over 12. Now only one of them means either A only or B only, but not both. Therefore still be the same, union minus intersection. Then I expand my union to come up with that. The next is to simplify and then substitute. So when I substitute, probability of A is that, probability of B is that, and this is that. Therefore now I have only one unknown, which is the intersection, and I have to make it the subject. And when I make it the subject, to be 1 over 12. So that is the probability that both events occur. What about the probability that none of them occurs? None of them means neither A nor B. Which is this, neither A nor B is given by that. And because the complement is outside, it means that it's the same as 1 minus probability of A union B. So expand this A union B to give you this, then substitute. Because the good thing, we now know the intersection. and then I'll come up with a half as the answer. So now there are some types of events which we need to know in a level. One of them is what we call exhaustive events. So when they say that two events are exhaustive, it implies that their union is equal to 1. So each time you see the word exhaustive, always remember that the union must be equal to 1. That is the condition for exhaustive. What about for mutually exclusive events? So when they say that two events are mutually exclusive, what should come in your mind is that their intersection is equal to 0. Those are the conditions. For exhaustive, union is equal to 1. For mutually exclusive, intersection is equal to 0. And we shall see how helpful these conditions are. So let's first go through the questions which require those two events, then we shall go to the other type of event. So question 1 says, for events A, B and C, probability of A is 0.28, probability of B is 0.66, probability of C is 0.49, and probability of A union B is 0.86, probability of A union C is 0.77, and probability of B union C is 0.92. Find each of the probabilities below and state whether each pair of events is mutually exclusive. Now you should remember that mutually exclusive, it means that the intersection must be equal to 0. Therefore, we have to get the intersection of A and B. From this law or universal or union of events, we can come and substitute for the union A union B, then probability of A and probability of B. And when I make A intersection B the subject, I'll come up with this. Now, because it is not equal to 0, it implies that they are not mutually exclusive. So that is why I told you that when they talk about mutually exclusive, always remember that the intersection must be 0. So that is event A and B. What about event A and C? So we shall do the same for event A and C. So still start from the union of events, then substitute, and then make the intersection the subject. It is 0, that means that A and C are mutually exclusive. Then Roman C still, B and C, start from by stating the union of events, then substitute and make the intersection the subject. So it then conclude that it's not equal to 0, meaning that they are not mutually exclusive. So that is what mutually exclusive means. Intersection has to be equal to 0. Then question 2 says, if X and Y are mutually exclusive events with probability of X equal to 0.48 and probability of Y equal to 0.37, find Roman 1 probability of X intersection Y, X union Y, and X complement intersection Y complement. So number 1, because they are mutually exclusive, you must remember that it is equal to 0. Then for Roman 2, union, you should remember that the intersection is 0, so what remains is just X, probability of X plus probability of Y, which gives you 0.85. Then for Roman 3, this one, like I said, this was under De Morgan's law. So De Morgan's law means that if this complement comes out, then this sign has to change to this. Now, why aren't we showing the complement here? It is because of this 1 minus, because probability of X minus X, probability of X union Y complement is the same as 1 minus probability of X union Y. So because we have started by saying 1 minus, that is why we are not seeing the complement here. So substitute for union and then come up with this as the answer. So question 3 says, for events C and D, probability of C complement is 0.6, probability of D is 0.25, and probability of C intersection D complement is 0.4. Roman 1, show that C and D are mutually exclusive. And Roman 2, find the probability of C union D. So we have to show that we have to first get C intersection D and see if it is equal to 0. So first of all, we are given C complement, therefore probability of C is equal to 1 minus probability of C complement, which is 0.4. Then C intersection D is equal to probability of C minus probability of C intersection D complement. So this is got from contingency table. So substitute for C and C intersection D complement to come up with 0, and because it is equal to 0, it implies that these events C and D are mutually exclusive. They also ask for C union D, so C union D will be equal to probability of C plus probability of D. Because the intersection is 0, that's why you don't show it here, which gives you 0.65. Then question 4 says, Fred occasionally likes to wear a bright colored tie to work. On a given work day, he wears a gray tie, navy tie, orange tie, or red tie, with probability 0.6 for gray, 0.35 for navy, 0.03 for orange, and 0.02 for red. Find the probability that on a given work day his tie is orange or red. So you are coming and say that let R denote that he wears a red tie and O denote that he wears an orange tie. So these two events are mutually exclusive. Now mutually exclusive, it means that if two events are mutually exclusive, it means that they cannot happen at the same time. That is why we say that their intersection is equal to 0. Therefore probability of R union U is equal to probability of R plus probability of O. So here, let's first say the corresponding ones. Gray is this, navy is this, orange is this, and red is this. Therefore probability of red is 0.02, probability of orange is 0.03, so when I add the two I'll come up with 0.05. So that has been mutually exclusive events. Now we shall go to another type of event which we call dependent events, or what we call conditional probability. So a probability is conditional if it depends on what has already happened or what has already occurred. The probability that an event B happens given that an event A has already happened is called the conditional probability of B given A. So probability of B given A has occurred. And in mathematical symbol we write it as B/A. So probability of B/A means that probability of B given that A has already occurred. So when you see this slash, just remember that it is a conditional probability. Some students confuse it and they think it is B divided by A, which is not okay. So this probability of B given A can be worked out using the formula that probability of B given A is equal to probability of A intersection B over probability of A. So the good thing is that this formula is also available in your mathematical logbook. But what you should remember is that the numerator is the intersection of these two events, and the denominator is the probability of what has already occurred. So in this case, it is A which has already occurred, so that's what we put as the denominator. And like I told you from De Morgan's law, from commutative law, is that probability of B intersection A is the same as probability of A intersection B. So whether you write B intersection A or you write A intersection B, it is still the same. So now we shall go to what we call Bayes' theorem. So we have seen from conditional probability or from dependent events that if it is a/b, it implies the numerator will be intersection and denominator will be what has already occurred. So when I make this intersection the subject, I'll come up with this times this, which is here. Then also here, numerator is the intersection, denominator is what has already occurred. When I make the numerator the subject, I'll come up with this times that. Now these two are the same, therefore I can equate this to this, and when I equate, I'll come up with this. So this is what we call Bayes' theorem. What you should remember is that this conditional probability is multiplied by what has already occurred. Conditional probability is multiplied by what has already occurred. That is what you should always remember in Bayes' theorem. So similarly, if we put complements, you have to maintain your complements. For example, if I put a complement on B, it has to be maintained where there is B. If I put a complement on A, it has to be maintained each time I write A. And if I put a complement on both, it has to be maintained on both. So with that, we shall go through some questions. So question 1 says, if probability of G is equal to 0.7, probability of H is 0.63, probability of G intersection H is 0.24, find Roman 1, probability of G given H has already occurred, or probability of G/H. It is up to you to pronounce it any way you want. You can either say probability of G/H or probability of G given H has already occurred. So that one means that the numerator, it will be G intersection H, and denominator will be what has already occurred, which is H. Now the intersection, it was given, and also the probability of H was given. So when I divide, I'll come up with this as the answer. What about probability of H/G? So numerator is still intersection of G and H, and denominator is what has already occurred, which is G. So intersection is here and probability of G is here. So when I divide the two, I'll come up with this as the answer. Then question 2 says, if probability of A is 0.68, probability of B complement is 0.44, probability of C is 0.44, probability of A intersection B is 0.34, probability of A intersection C is 0.16, and probability of B intersection C complement is 0.49. Find this, this, and that. So let's start with the Roman 1, probability of B/A. So B/A, numerator is the intersection, and denominator is what has already occurred. So substitute the intersection and probability of A to give you a half, which they want. Then Roman 2, A/C. So still intersection goes in the numerator, and what has already occurred goes in the denominator. Then you substitute for intersection and probability of C to come up with 4/11, which they wanted. Then C complement/B. Still numerator is intersection and denominator is what has already occurred. So B intersection C complement, it is here, so just write it. Then probability of B, the good thing we have the probability of B complement, so I can easily get the probability of B by saying 1 minus that complement. And when I use the calculator, I'll come up with 7/8 as the answer. Then question 3 says, given that probability of X is 0.44, probability of Y complement is 0.72, probability of Z is 0.61, probability of X/Y is equal to 0.75, probability of Z/X is 0.25, probability of Y intersection Z complement is equal to 0.2, and probability of X intersection Y everything/Z is equal to 7/61. Find this, and that. Okay, so let's start with Roman 1, probability of Y. So we are given probability of Y complement, which is here. Therefore, probability of y is good by 1 minus probability of y complement, which is 0.28. Then for Roman 2, the probability of x intersection y. So x intersection y, from Bayes' theorem, it will be probability of y times probability of x slash y. Like I told you, what has already occurred is what you multiply by the conditional probability. So probability of y is here, probability of x slash y is there, which gives you 0.21. Then for Roman 3, the one probability of x intersection z. So still, from Bayes' theorem, what has already occurred is what we multiply by the conditional probability. The probability of x is this, probability of x z slash x is that, which gives you 0.11. Then Roman 4, y slash z complement. So y slash z complement, the intersection is y intersection z complement, and the what has already occurred is z complement. So I'll substitute. The good thing in the question, I have probability of y intersection z complement, which is 0.2, which is here. And also probability of z, I already know it. If we'll come here in the question, probability of z is 0.61. Therefore the complement can be got by saying 1 minus that probability, and in the end I'll come up with 20/39 as the answer they want. Then for Roman 5, the one probability of x intersection y intersection z. So still from Bayes' theorem, probability of this is what has already occurred, so that is what I multiply with the conditional probability. And the good thing, the whole of this conditional probability, I know it is there in the question. So if we come here, we're told that probability of x intersection y everything slash z is 7/61. 7/61, which is here. And probability of z, we got it from, where's probability of z? Okay, yeah, it was given the question and it was 0.61. Therefore, when I multiply, I come up with 0.07, and that's what they wanted. Then now shall go to question 4, which says two events A and B are such that probability of A is this, probability of B is that, and probability of A slash B is this. Calculate the probabilities that Roman 1, both events occur, Roman 2, only one of the two events occur, and Roman 3, neither events occur. So we shall start with both events occur, which is intersection. So both occur is the probability of A intersection B, which is given by probability of B multiplied by probability of A slash B. So multiply by B because B is what has already occurred. So probability of B is that, probability of A slash B is this, which gives you 1/15. Then for Roman 2, probably that only one of the events occur. So only one means A only or B only, but not both, which is union minus intersection. So union minus intersection to give you 11/15. So that was Roman 2. What about Roman 3? For Roman 3, probably that neither events occur. Neither means complement of the union. So complement of the union is this, which is 1 minus A union B, which is 1 minus 4/5, which gives you 1/5. So now we shall go to question 5, which says that events A and B are such that probability of A is 0.7, probability of B is 0.2, probability of A slash B is 0.1. Find the probability that Roman 1 both of the events will occur, and Roman 2 exactly one of the events will occur. So we shall start with Roman 1 both, which is intersection. So intersection B will be probability of B times probability of A slash B, which gives you 0.02. Then for Roman 2, exactly one of the events occur. That means A only or B only but not both, which is union minus intersection. Therefore, when I expand the union, when I expand the whole of this, gives you this. And next is to substitute to come up with this 0.86 as the required answer. Then question 6 says events A and B are such that probability of A union B is 7 over 10, probability of A slash B is 7 over 12, and 4 times probability of A is equal to 3 times probability of B. Find Roman 1 probability of A intersection B and Roman 2 probability of A union B complement. So let's start with Roman 1. So first of all, from this statement we can make A the subject to come up with this. Is when I bring this for this side, becomes 3 over 4, which is 0.75. So I've got probability of A in terms of probability of B. Therefore I'll come here and say that probability of A intersection B is equal to probability of B times probability of A slash B. So now here probability of A slash B is 7 over 12, which is here, and probability of B I don't know it yet. So I have two equations with B. I've expressed probability of A in terms of probability of B, and also I've expressed the probability of A intersection B in terms of probability of B. Therefore, in this union I can come and substitute. So substitute this for A and substitute this for intersection, to remain with only one unknown, which is probability of B. Now next is to collect like terms and make probability of B the subject. So when I make it the subject, I'll come up with this as the answer. So that is probability of B. Now that I've got probability of B, I can go back to equation 2 and get my probability of A intersection B, which they want. So where there's probability of B, I'll put there 3 over 5 to give me 7 over 20 as the required answer for Roman 1. Then for Roman 2, they want A union B complement. So first of all, A intersection B complement from Contingency Table, it is probability of A minus probability of A intersection B. So probability of A we already saw that it's equal to 0.75 probability of B, and A intersection B is, we have already got it here as this. So I come and substitute for probability of B to come up with this. Then from there I have to use the calculator to simplify the whole of this to give me 1 over 10. So now that I've got the intersection, I can now come and get the union. So probability of A plus probability of B complement minus probability of A intersection B complement. So come and substitute. Where there is A intersection B complement, I'll put there this. Where there is probability of A, I'll put there this, because when I multiplied this, I come up with 9 over 20, which is probability of A. Then for probability of B complement, I'll say 1 minus probability of B to give you that. So in the end, I'll come up with 3 over 4 as the required answer. So that was dependent events. Now we shall go to probability tree diagram for dependent events. So we are still under dependent events. So tree diagrams show probabilities for sequences of 2 or more events. Therefore, if event A occurs first and then event B occurs, then the tree diagram will be in this form. So this will be probability of A complement. Then here it means that I want probability of B given that probability of A has occurred. Here I want probability of B complement given probability of A has already occurred. That's why I write this. Then here I want probability of B given A complement has already occurred. That's why you write this. And here I want probability of B complement given A complement has already occurred. That's why you write this. So this times this will give me the probability of A intersection B. This times this gives you the probability of A intersection B complement. This times this gives the probability of A complement intersection B. And this times this gives the probability of A complement intersection B complement. And I think you have already seen that under Bayes' theorem. So these are the rules we need to follow when dealing with tree diagrams for dependent events. One is that to find probability of a sequence of events, you multiply along the branches, the branches representing those events, just like we saw here, like I said. Then for rule 2, the total sum of the probabilities at every junction is equal to 1. Therefore this is equal to 1, this is equal to 1, this is equal to 1 from our tree diagram. Then rule 3, the total of the n probabilities is always equal to 1. So when I add all these probabilities which I got from my tree diagram, I must come up with 1. So with that we shall go through these questions. Question 1. 2 boxes A and B contain 1 red, 4 white and 3 red, 2 white cards respectively. So box A has 1 red and 4 white, and box B has 3 red and 2 white. A box is picked at random and then a card is picked. Part A, what is the probability that a white card is picked? And part B, if, note this word if, a red card is picked, what is the probability that it is from box A? So this one has this one is a dependent event, as you have seen the solution. So first we have to draw our tree diagram. Let's first draw the branches. So there are 2 boxes A and B, so one I can pick from A or box B. Then from box A I can either pick red or white, and from box B I can also pick either red or white. Now because there are only 2 boxes, the probability of picking box A is a half, and also picking box B is a half. Then from box A there is 1 red, so probability of picking red will be 1 over 5, which is the total, and probability of picking white will be 4 over 5, which is the total. Then for box B there are 3 red, so probability will be 3 over 5, and 2 white, meaning the probability will be 2 over 5. So that is our tree diagram. Next is to answer the questions. One is the probability that a white card is picked. So probability of picking white can be this or this. So for this one it means A intersection W, and this means B intersection W, which is this and that. Now for A intersection W it will be this times this, which is here. Then for B intersection W it will be this times this, which is here. And in the end I'll come up with 3 over 5 as the answer. Now part B said, if a red card is picked, what is the probability that it is from box B? So this one, it means that this one has already occurred, therefore it will be probability of box B given a red card has already been picked. So you should note the order. It is B/R. If you write R/B, it is not okay because they want probability of picking from box B. So this is the probability they want, but this one has already occurred. Therefore, expanding this numerator becomes the intersection, and denominator is what has already occurred. So B intersection R, right, will be this times this, which is here. Then probability of R, remember probability of R, there are only 2 balls, there is white and red, so we already got the probability of white, therefore the complement will be probability of red. That's why you see 1 minus probability of white, and in the end I'll come up with 3 over 4 as the answer. Then question 2 says Uganda Meteorological Center Meteorological Center records indicate that the probability that a particular day is dry is 3/10. Uganda Cranes records of success are better on dry days than on wet days. The probability that the Ukrainians win on a dry day is 4/7, whereas the chance that they win on a wet day is 3/11. Cranes is due to play their next match on Saturday. Roman 1, what is the probability that the Cranes will win? Then Roman 2, 3 Sundays ago, the Cranes won their match. What is the probability that it was dry? So you start with the Roman 1, probability that Cranes win. So dependent events, if there is a sequence, you can use tree diagram, which I also advise. So first they talked about dry, then winning. So it can be, so D means dry and D complement means it is not dry, in other words it is wet. Then here it means that it wins given that it was dry, or it loses given it was dry. Here it means that it wins given it was not dry, and it loses given it was not dry. The probability of dry, it was 3/10. That's what was given in the question. Therefore not dry will be 1 minus 3/10, which is 7/10. Then probability of winning on a dry day, it was 4/7, it was given in the question. Therefore not winning, it will be 1 minus 3/7, which is 3/7. Then winning on a wet day, it was 3/11. Therefore losing will be 1 minus this, which is 8/11. So now that I've filled the table, I can go and answer the questions. Question 1 is the probability that Cranes will win. So win is here. There is this win and also this win. The first win is D intersection W, and second win is D complement intersection W. So D intersection W, it is this times this, which is here, and D complement intersection W, it is this times this, which is here. So using a calculator, I'll come up with this as the answer. Then for Roman 2 says 3 Sundays ago the Cranes won their match. What is the probability that it was dry? So here it means that winning already occurred, and the probability they want is for dry. Therefore it will be probability of dry given win. Like I told you, the order matters. So shall come here and write the probability of dry given win already occurred. Therefore intersection is the numerator, denominator is what has already occurred. So we have already got the probability of winning as this, and that's what we write under winning. Then intersection, we already saw it, D intersection W, it was this, which simplifies to this. That's why we write it here. And in the end we shall come up with 44/93 as the required answer. Then question 3 says a student may travel to school by car, by bicycle, or on foot. The probability of using a car is 1/3, of riding is 1/2, and of going on foot is 1/6. When the student uses a car, the probability of arriving in time is 3/4. By bicycle is this, arriving in time when he uses a bicycle is 2/5, and arriving on time when he's on foot is 1/10. Calculate the probability that the student, Roman 1, arrives in time, and Roman 2, went on foot given that he did not arrive on time. So let's start with Roman 1. So we shall come and let C to denote car, B to denote bicycle, and F to denote foot, then T to denote arriving on time. So it is easier if you use tree diagrams. So there are three options. There is car, bicycle, and foot. And for each they can arrive on time or you don't arrive on time. So we are given the question the probability for using a car is 1/3, bicycle is 1/2, and foot is 1/6. So that's what you shall write here. So for car it is 1/3, for bicycle is 1/2, and for foot is 1/6. Then here we are told that when the student uses a car, the probability of arriving in time is 3/4, bicycle is 2/5, and foot is 1/10. Therefore we shall come here. For car it was 3/4, then complement is 1/4. For bicycle it was 2/5, complement is 3/5, and for foot it was 1/10, complement is 9/10. Therefore we shall now answer the questions. Question 1 said the probability that he arrives in time. So arriving in time, we have three options. There is this, there is this, there is this. Therefore you shall come and write all of them: C intersection T, B intersection T, and F intersection T. For C intersection T we shall say this times this, which is this first bracket. For B intersection T it will be 1/2 times this, which is this. And for F intersection T we shall write this times this, which is here. And in the end we shall come up with 7/15 as the probability. Then for Roman 2, Roman 2 said find the probability that a student went on foot given that he did not arrive on time. So not arriving on time already occurred, and the probability they want is that he went on foot. Therefore to be F/T complement. The numerator is the intersection, denominator is what has already occurred. So F/T complement, there is this F and there is this T complement, therefore this times this gives you that numerator. Then you already saw the probability of T, therefore T complement will be 1 minus that. And simplifying gives you 9/32, which they wanted. Then question 4 says 2 bags contain colored balls as shown in the table below. So is the table. A die is thrown. A die is thrown, and if a 1 or a 6 appears, then bag 1 is chosen. Otherwise, bag 2 is chosen. So this is the condition for you to get the probability of picking either bag 1 or bag 2. A ball is then drawn at random from the selected bag. If a white ball is drawn, what is the probability that it came from bag A? So here it means that white already occurred, and the probability they want is that it came from bag A. So we shall come here and say probability of picking bag 1 is choosing either a 1 or a 6. So choosing 1 is 1/6 and choosing a 6 is 1/6, because there is only 1 1 and also 1 6 in a die, which gives you 1/3. Then probability of bag 2 is the complement, which is 2/3. Now that I've got that, I can draw my tree diagram. So for each bag it has those three options. It has red, white, and blue. Therefore for bag 1 it is 1/3, which is here, and bag 2 it is 2/3. Now when I choose bag 1, remember bag 1 has 3 red, 2 white and 1 blue. Total is 6. Therefore, for red it will be 3 over 6, for white it will be 2 over 6, and for blue it will be 1 over 6. What about bag 2? So bag 2, it has 0 red, 4 white and 2 blue, which is a total of 6. Therefore here I'll come and say that for red it is 0 over 6, for white it is 4 over 6, and for blue it is 2 over 6. So now that I filled the tree diagram, I can answer the question. So the probability, this is the probability they want is conditional, but for you to get it you must first get the probability of picking a white ball. That's what we are doing here. So probability of picking a white, it can be from bag 1 or from bag 2. So it is white is here, white is here. So bag 1 to be this times this, and bag 2 to be this times this. So when I multiply the two, I come up with this and that, which gives you 5 over 9. And the probability they want is probability of bag 1 given that it was white. So therefore numerator will be the intersection and denominator will be what has already occurred. So this intersection, you already saw it here, which is this, and it was simplified to this. That is why you see 1 over 9 here. Then for W, it is here, that's why you see it there. So in the end we come up with 1 over 5 as the required answer. So now we shall go to question 5. Question 5 says, a machine has 3 components A, B, and C. The probability of A working is 7 over 10, and if A is working, the probability of B working is 3 over 5. Now note this, if. Now this word if is very vital. It means it is a condition for you to get this B. Therefore it is a dependent event. Then if A is not working, then probability of B is 1 over 3. If A and B are working, the probability of C working is 5 over 6. Otherwise it is 1 over 10. The machines only work if C is working. Roman 1. What is the probability that the machine is working? So in other words, they want the probability that C is working. So let's first start with the Roman 1. So like I told you, for dependent events it is easier if you use the tree diagram. So we shall let WA, WB, WC to denote that WA for A is working, WB for B is working, and WC for C is working. Now first of all it was A, followed by B, followed by C. So here for probability of A is working is 7 over 10. It was given here. They told you that probability of A working is 7 over 10. And this complement will be 3 over 10. Then what about B working? Here they told us that if A is working, the probability of B working is 3 over 5. That is why you see this 3 over 5 here, because A is working. The complement will be put here, which is 2 over 5. So next is this 1 over 3. Let's see where it came from. So 1 over 3, they told us that if A is not working, then the probability of B working is 1 over 3. So A is not working, this is WA complement. The probability of B working is 1 over 3. And this complement will be put here, which is 2 over 3. The next is this 5 over 6. Where is it coming from? They told us that if A and B are working, the probability of C working is 5 over 6. otherwise it is 1 over 10. So if both this and this are working, then this probability will be 5 over 6. Its complement will be put here, which is 1 over 6. Otherwise it is 1 over 10, so this one to be 1 over 10 here, complement is 9 over 10, and here it will be still 1 over 10, complement is 9 over 10, here 1 over 10, complement is 9 over 10. Okay, so that is a tree diagram. Next is to answer the questions. So part A said, what is the probability that the machine is working? So working means that C has to work. So C working, we have this, we have this, we have this, we have this. So we shall get all those. So there is this 1, 2, 3, and 4. Therefore, we shall come and substitute. For this is that, for this is this, for this is this, and for this is that. Then use a calculator to come up with this as the probability of C working. Therefore, the machine working is 51 over 125. Then for Roman 2, given that A is working, so this is a condition, what is the probability that only one of B and C is working? So this is the probability of they want, and what has already occurred is A. Only one of B or C, so either B or C is working. So it's a conditional probability, and we shall state it in that form. Here it means that only is B working, and this means that it is C working. And what has already occurred is A working. So expanding this is this, expanding this is that. Then substituting gives you that. Substituting for this is this, for this is that. Then simplifying and gives you this 7 over 50 as the final answer. Then Roman 3, if C is working, what is the probability that B is working? So that means that it's also a dependent event. So C is it's already known that C is working. The probability of B working, if C is working, is written by this. Expand, numerator is the intersection, denominator is what has already occurred. Therefore you shall come and substitute. So substituting gives you that. So this one we already got it as this. Then here we already got the whole of this as this, and the whole of this as this. So simplifying gives you 15 over 17. So we have been dealing with dependent events, but now we are going to what we call independent events. So under dependent, we saw that the occurrence of one event affects or influences the occurrence of the other. Therefore, for independent, it is the opposite. Therefore, two events are said to be independent if the occurrence or non-occurrence of one event has no influence on the occurrence or non-occurrence of the other event. For example, if a dice is rolled twice, and events A, where the first roll is a 4, and event B, where the second roll is a 4, are independent. Why? Because the number rolled on the second roll does not depend on the number rolled on the first roll. So it is not a must that if I first roll a 4, even the second time when I roll again I'll have to get a 4. That's what we mean by independent. The occurrence of one does not affect the occurrence of the other. Let's also look at another example. So suppose a card is selected at random from a pack of cards, then replaced, and a second card is selected at random also. Then if event A is that the first card is a 7 and event B is that the second card is a 7, these two will be independent because the probability of B, or the probability of picking a 7 on the second trial, is not affected by what was selected at first. It's not a matter that when you first pick a 7, even the second time you will pick a 7. So that's what we mean by independent events. Therefore, if events A and B are independent, it implies that their intersection is equal to the product of the individual probabilities. So if you have events A and B, then it implies that probability of A intersection B is equal to probability of A multiplied by probability of B. So this is the condition for independent events. I think you remember we saw the condition for mutually exclusive that the intersection is 0, but now here for independent, the intersection is the product of the individual probabilities. Therefore, the union of two events become, here where there is intersection, you shall put there the product of the two independent events. So when you put a complement, it still remains the same. If events A and B are independent, it implies that even their complements are independent. Therefore, A intersection B complement will be equal to this, and A complement intersection B will be equal to this product, and this intersection this will be equal to this product. So there's something we need to note under independent events, that if events A and B are independent, then the probability of B is the same whether A happens or does not happen. So what does that mean? It means that when we come to our conditional probability, remember this was the probability of B given A has occurred, and this is the probability of B given A has not occurred. Now when it comes to independent events, whether A has occurred or has not occurred, the probability of B must remain the same. So that is why this probability of B when A has occurred is equal to the probability of B when A has not occurred. Similarly, the probability of A when B has occurred and probability of A when B has not yet occurred, they will be equal because we are dealing with independent events. Note that you should note that this one only works when the events are independent, and they will always specify in the question that the event is independent, or it is mutually exclusive like we saw, or it is exhaustive. So with that, let's go through these questions. Question 1 says, if A and B are independent, I think it's what I told you, so they will always specify that the events are independent. So I say that if events A and B are independent, show that Roman 1 events A and B complement are also independent, and also show that events A complement and B complement are also independent. So you already saw that when two events are independent, even their complements are independent. So in this question, they want you to show that it is true. So let's start with Roman 1. For Roman 1, we shall come and remember that if these two are independent, then their product, so their intersection, is equal to the product of the individual probabilities. Therefore, for these two events to be independent, which they said here, it implies that also their product must be, their intersection must be equal to the product of the individual events. So product of that means that probability of A multiplied by probability of B complement. So in other words, this is what they want you to show. Now let us start from the left hand side to show that this one is equal to this. So if you start from the left hand side and we use the contingency table, we shall realize that this is equal to probability of A minus probability of A intersection B. I think realize that, like I told you, for contingency table, what is here does not change. So this is A, it is A here, and it's also A here. But what is not here changes. So this is B complement, this is B. That is the trick you can use to memorize the contingency table. But you already know that these two are independent. It was already given to you in the question. So that means that their intersection is equal to the product of the individual probabilities. So what we shall do, we shall come here and replace this intersection with the product of the individual probabilities. Then from there we shall realize that probability of A is common. So we shall pull it out. Then here we shall remain with 1 and here we shall remain with probability of B. Now we already know that 1 minus probability of B is equal to probability of B complement. And this is the product which shows that events A and B complement are also independent. So that was Roman 1. Let's now go to Roman 2, where they want you to show that events A complement and B complement are independent. So for these two events to be independent, it implies that the intersection is equal to the product of the individual probabilities. So this is what they want you to show. Still we shall start from the left hand side. So this one is equal to this, and from De Morgan's law it implies that when this complement moves out of the bracket, the sign here must change. It was intersection, it becomes union. I think you remember that from De Morgan's law. Then from here, this is the complement, so it implies it's the same as 1 minus probability of A union B. But you already know the expansion of A union B, that's equal to probability of A plus probability of B minus probability of A intersection B. And you already know that these two events A and B are independent, therefore we shall replace the intersection with the product of the individual probabilities. Then from there we can open brackets to come up with this, and after that it is you to choose what you want to pair. If I pair this with this, I can pair this with this and also this with this, or I can choose to pair this one with this B and then this with this. Any is okay. So in this case I've chosen to pair these two alone and also these two alone to come up with this. So that means that here it becomes 1 minus probability of A. Then here, remember, this is minus and this is a plus. So when I put a minus outside, here it must also be a minus, so that when I open brackets, it becomes positive, which is here. Therefore here, I pulled out negative B, which is here. So this remains positive 1 and here it remains negative probability of A. Now you realize that this and this are common, and they are the same, and they are the complement. So this is the probability of A complement and this is also probability of A complement. So when I factorize it out, here I remain with 1 and here I remain with probability of B. Now 1 minus probability of B is equal to probability of B complement. So in that case we have shown that these two events are also independent. So that was question 1. Now we shall go to question 2. So question 2 says, if A and B are independent events, find probability of B given that probability of A is 0.4 and probability of A union B is 0.8. So I'll first expand the A union B. Then I'll remember that these two are independent, therefore I'll replace them with the product of the individual probabilities. Then from there, I remember what I was given. I was given that probability of A union B is 0.8 and probability of A is 0.4. So in that case, I realized that I have only one unknown, which is probability of B. So my aim is to look for a way of making it the subject. Now when I make it the subject, it becomes 2/3, and that will be the probability they wanted. Then question 3 says, given that A and B are independent events in a sample such that probability of A complement is 3/5 and probability of A union B is 4/5, find Roman 1 the probability of B and Roman 2 the probability of A complement union B complement. So first of all, I know that I'm given A complement, so I can be able to get the probability of A by saying 1 minus probability of A complement, which gives me 2/5. Then I remember that A union B is equal to probability of A plus probability of B minus the probability of A intersection B, which is the product of the individual probabilities, and it is because we were told in the question that they are independent. Then I'm going to substitute what is given. A union B is given, A is given, A is given, so I'll have on the probability of B, which is unknown. So my aim is to look for a way of making it the subject, and when I make it the subject, probability of B will be 2/3. So that is Roman 1. Roman 2, the one probability of A complement union B complement. So from De Morgan's law, when these complements come out, the sign here changes. So it was union, it becomes intersection. Then I remember that this one is the A and B are independent, so it becomes the product of the individual probabilities. And also here, why have I put 1 minus? It is because of this complement. This complement means that all of this is equal to 1 minus probability of A intersection B. So probability of A intersection B is here and 1 is here. Now the good thing, I know probability of A and probability of B, so when I substitute, I'll come up with the required probability as 11/15. Then question 4 says A and B are independent events such that probability of A is 0.35, probability of B is X, and probability of A union B is 0.74. Find Roman 1 the value of X, and Roman 2 probability of A intersection B complement. So first of all, I'll first expand the A union B. Then I remember that these two are independent, so I replace them with the product of the individual probabilities. Then substitute what is given. So A union B is given, and probability of A is given, and probability of B is given as X. So I only have X, therefore I have to look for a way of making it the subject, and X will be equal to 0.6. That was Roman 1. What about Roman 2? Roman 2, the one probability of A intersection B complement. So still from contingency table, probability of A intersection B complement is equal to probability of A minus probability of A intersection B. Then I'm going to substitute. Probability of A is this, which I'll put here and here, and probability of B is X. Therefore in the end I'll come up with this as the required probability. Then question 5 says A and B are events such that probability of A is 2/5, probability of A intersection B is 1/4, and probability of B slash A complement, or probability of B given A complement has occurred, is 5/8. State probability of B complement slash A complement, and hence determine Roman 1 probability of A union B and probability of B. Then Roman 2, show that A and B are independent. So we shall start by stating. So stating this is equal to, Roman numerator is the intersection and denominator is what has already occurred. Then Roman 1, they want you to get this and this, so we shall first get intersection. So probability of B intersection A complement is equal to probability of A complement multiplied by probability of B given A complement has occurred. So we are using this because in the question we are given here, so we move from known to unknown. Therefore I substitute probability of A is here, so getting A complement I'll have to say 1 minus probability of A. Then B slash A complement is 5/8. In the end I'll come up with this as the probability of B intersection A complement. So now I'll come and get the probability of B which they wanted. So using from contingency table, probability of B is equal to probability of B intersection A plus probability of B intersection A complement. Like I told you, what is here does not change. So I already know this intersection, which is here, so I'll come and put it there. Then I already know this intersection, so I'll come and put it here. When I add the two, I'll come up with the probability of B which they wanted. What about probability of A union B? So I'll first expand, then substitute, and then come up with the probability of A union B which they wanted. So that was Roman 1. Now we shall go to Roman 2, where they want you to show that events A and B are independent. So for independent events, we shall remember that the intersection is equal to the product of the individual probabilities. So what we shall do, we already know the intersection, we know the probability of A and probability of B. Now the question is, are they equal? So because they are equal, it implies that they are independent, and by that you will have shown. The next is question 6. Question 6 says, two hunters A and B shoot at an animal. The probability that A hits the animal is a half, and the probability that B does not, know this word, does not hit the animal is a third. A shoots at the animal first, then B. Find the probability that, Roman 1, both A and B hit the animal. Then Roman 2, only one hits the animal. So this is the interpretation of what is given. Probability of A is a half, probability of B complement, because they say it does not hit, that is why there is a complement, is a third. Therefore probability of B is 1 minus the complement, which gives you 2/3. Now A and B are independent events because the occurrence of one does not affect the occurrence of the other. Therefore that means that probability of A intersection B is equal to probability of A times probability of B. Therefore come and substitute for probability of A and probability of B to give you 1/3. Then Roman 2, only one hits. So only one means union minus intersection. I think you remember that under the all situations. So A union B, when you expand, I'll come up with this with a 2 here. Then I'll come and substitute for probability of A, probability of B, which is here. Then this 2 is here. Then the intersection, we already got it here as this. So in the end, I'll come up with a half as the required probability. So now shall go to question 7. It says that two independent events A and B are such that there is a probability of 1/6 that they will both occur, and a probability of 1/3 that neither will occur, neither A nor B. Find part A, probability of A, part B, probability of B. So first of all, we shall let probability of A to be X and probability of B to be Y. Therefore, probability that both occur is the intersection, and they told you it is 1/6. And also these are independent events, that's why we put a product here. So when I substitute, probability of A is X, probability of B is Y. So I'll come up with equation 1 with 2 unknowns. That means I have to get another equation with also the same unknowns. Therefore I'll come and say that neither will occur means the complement of the union. So complement of the union will be a third. And it gives you 1 minus probability of A union B. And I already know, so what I will do, I'll come and substitute. So when I make this one the subject, I'll bring this one this side and bring this one this side. So I'll come up with probability of A union B equal to 1 minus a third, which gives you 2/3. After that, I'll expand the union and then substitute. So substituting, probability of A is this, the union is 2/3, and B is this, and we already saw that the intersection is 1/6. Therefore I'll come and make Y the subject and y will be equal to this. Therefore, these are two equations and two unknowns. Can either use substitution or elimination, but substitution is easier. That is why I've made y the subject. So that means that I'll get this y and substitute it here in equation 1. So I'll come and say that substituting equation 2 into equation 1, I'll come up with this. Where there is y, I'll put there that. Then now I have one unknown, so I'll have to expand and look for a way of solving it. So this is a quadratic, therefore I have to rearrange and get the values of x. So the values of x will be, one will be a third, another one will be a half. Now for x equal to a third, I have to get the corresponding value of y, which will be a half. And for x equal to a half, the corresponding value of y will be a third. Therefore, I come and say that probability of A is a third when probability of B is a half, or probability of A is a half when probability of B is a third. So now we shall go to what we call sampling. So in most cases, the outcome space is too large, and we are forced to use some samples randomly selected from the outcome space. The new collection of possibilities is what we call the sample space. There are two methods of sampling from a discrete set, that is, sampling with replacement and sampling without replacement. So let's start with sampling with replacement. So this is an example of independent events. That's what you should know. Then in each case, we replace the first item before we select the second item. So this is the condition for sampling with replacement. You sample, then you first replace it back before you sample again, or the second time. So in fact, that means that we can even pick the same item over and over again. But this is impossible when we sample without replacement, as we shall see in the next part. So let's first do an example for sampling with replacement. So question 1 says, two balls are picked from a box, one at a time, with replacement. The box contains 4 red and 2 black balls. Find the probability that Roman 1, the second ball is red, and Roman 2, both balls are black. So here I shall need a tree diagram. So we have 4 red and 2 black. Therefore, if I first pick red, it implies that I'll pick 4 out of the 6. That is why it is 4 over 6. And here it will be 2 out of 6, which is there. Then here, because it was with the replacement, it remains the same throughout the red. So that's why here there is also 4 over 6. And here there is also 2 over 6. And here there is 4 over 6. And here there is 2 over 6. So it doesn't change. Therefore, probably that the second ball is red, sorry. So red means that I'll need this and this. Therefore, it will be R1, R2, which is here, and B1, R2, which is there. So you come and substitute red R1, R2, there is this times this, which is here, and B1, R2, there is this times this, which is here. So now use a calculator, I'll come up with 2 over 3, and that's what they wanted. Then Roman 2, both balls are black. That means we're interested in this and this. Therefore, I'll come and say B1 intersection B2, which is this times this, which is here, which gives you 1 over 9. So now we shall go to sampling without replacement. So this is an example of dependent events. Remember, sampling with replacement was an example of independent event. But now this one is an example of dependent events. So each sample could be considered as being taken by first selecting one item at a time, and then, while keeping that item out of the population, the second item is picked. there is no that means that there is no chance of picking one item twice. Now here there are two methods for answering such questions, and one of the methods is by using the probability tree diagram, which you are well versed with. Another one is by using permutations and combinations. So the assumption is that you have already watched the video for permutation and combination in Math Paper 1. Remember, Math Paper 1 under Algebra, there is a topic called Permutations and Combinations. So I encourage you to first watch that video before you proceed with this video. So now we shall go to question 1. Question 1 says, a bag contains 5 black pens and 4 red pens. 2 pens are picked at random, one after the other without replacement. Find the probability that Roman 1, both pens are of the same color, and Roman 2, the second pen is red. So like I said, there are two methods and we shall look at both methods. So let's start with method 1, which is by using a probability tree diagram. So here if I first pick black, it implies the probability is 5 over 9 and the complement will be 4 over 9. Then if I pick black the second time, the probability will be 4 over 8. Why? Because this one reduces by 1 and also this one reduces by 1. And this complement will be 4 over 8. Then for this side, if I pick red, it implies that this one reduces by 1 and this one also reduces by 1 to get 3 over 8. And the complement is 5 over 8. So now we shall go to Roman 1. Both pens are of the same color. It means that they can both be black or both be red. So both black, it will be this times this, which is here. And both red, it will be this times this, which is here. And when I use the calculator, the probability will be 4 over 9. That was Roman 1. Then Roman 2, the one, the probability that the second pen is red. So that means we have this and this, which is B1 R2, which is here, and R1 R2, which is here. So when I substitute, it will be this times this, which is here, and this times this, which is here. So in the end, I'll come up with 4 over 9 as the required probability. So that has been method 1. Now we shall go to method 2 of using permutations and combinations. So method 2, Roman 1, same color. Now here, when the order does not matter, we use combinations, and when the order matters, we use permutations. So in this case, the order does not matter, they only want same color, so we shall use combinations. So same color means you can pick 2 black or you pick 2 red. So probability of picking 2 black, so to pick number of ways, so this n2 black means number of ways of picking 2 black, and this is number of ways of picking 2 red, and this is the number of all the possible outcomes. So 2 black, remember we have 5 black and 4 red. Now 2 black means that out of these 5 we need 2, so that is why we get 5 combination 2. And here out of these 4 we need 2, so that's why you get 4 combination 2. Then the sample space, out of the total, which is 9, so 5 plus 4 is 9. So out of the 9 we need 2 pens. That is why it is 9 combination 2. So next is to use the calculator. This gives you this, and this gives you this, and this gives you that. When you simplify, you'll come up with 4 over 9, which is the same as before. Then for Roman 2, the order matters, because the question said probably that the second pen is red. So when the order matters, we use permutations. So here that is the second, and this will be the first. So second pen is red. It means that out of the red, remember there were 4 red and 5 black. So the probability, the condition is that the second must be red. So out of this, you have to pick this second pen. You have 4 options. That is why there is 4 red there. But to pick this first one, you can either pick from these 5 or you pick from 3. Why is it 3 red? Because you have already picked red to fill this second position. Therefore, you are remaining with only 3 red. That is why there is 3R there. So that means that for this first one, it will be 8, because total of this is 8, 8 permutation 1. So when it is the orders needed, we use permutation. And for this one, it will be 4 permutation 1. Therefore, probably that the second one is red implies that is equal to number of ways of second red over the sample space. Second red will be this times this, which is here, over the total, which is 9, because the total, like I told you, we have 5 black and 4 red, so the total is 9. But out of the 9 we need 2, that's why we have 9 permutation 2. So using the calculator, this gives you 8, this gives you 4, and this gives you 72. And in the end you come up with 4 over 9, which is the required probability, and it's the same as before. So that is question 1. Then we shall go to question 2. Question 2 says a box contains 7 red balls and 6 blue balls. 3 balls are selected at random without replacement. Find the probability that Roman 1 they are of the same color, and Roman 2 at most 2 are blue. So we shall still use 2 methods. So let's start with method 1 for probability tree diagram. So there are 3 balls. Now let's fill this tree diagram. So if I pick red, it will be here 7 over 13, because 7 plus 6 is 13. Then the complement is 6 over 13. Then here, if I pick, it means that this one reduces by 1 and also this one by 1 to give you 6 over 12. And the complement is 6 over 12. Then when I come here, this one reduces by 1 and this one reduces by 1 to give you 5 over 12. And the complement is 7 over 12. That is the second picking. What about the third picking? Here, this one reduces by 1 and this one reduces by 1 to give you 5 over 11. And the complement is 6 over 11. Then here, this one reduces by 1 and this one reduces by 1 to give you 5 over 11. And the complement is 6 over 11. Then here, this reduces by 1 and this reduces by 1 to give you 6 over 11. And the complement is 5 over 11. Then here, this reduces by 1 and this reduces by 1 to give you 4 over 11. And the complement is 7 over 11. So now that we have filled the tree diagram, we can answer the questions. Roman 1 said probability that they are of the same color. So same color, all can be red or all can be blue. So this is all red and this is all blue. So all red will be this times this, which is here. And all blue will be this times this, which is there. So when I simplify, I'll come up with 5 over 26 as the required probability. That is Roman 1. What about Roman 2? For Roman 2, they want the probability that at most 2 are blue. So at most means 2 or less. Therefore, the complement will be that all of them are blue. And all blue, you already got it here as 10 over 143. So in the end we shall come up with 133 over 143 as the required probability. So that is method 1. What about method 2? So method 2, still same color, it will be number of ways when all the 3 are red plus number of ways when all the 3 are blue over the sample space. So here the order is not needed, that is why we are using combinations. So out of the 7 red we need 3, and out of the 6 blue we need 3. Then here the total 7 plus 6 is 13, so out of 13 we need 3 balls. So when I use the calculator, this gives you 35, this gives you 20, and this gives you 286. And then you shall come up with 5 over 26, which is as before. Then for Roman 2, at most 2 blue. At most 2 blue is the same as 1 minus probability of all blue. So all blue is the same as this over this, which is here. And 1 minus that gives you 133 over 143 as before. Then question 3 says a bag contains 30 white, 20 blue and 20 red. 3 balls are drawn one after the other without replacement. Determine the probability that the first ball is white and the third is also white. So still we shall use 2 methods. Let's start with the method of a tree diagram. Okay, so we shall now fill our tree diagram. So starting with this, it will be 30 over 70, and here it will be minus 1 to give you 29, minus 1 to give you 69, so it gives you 29 over 69. Then here you remain with 20 because it didn't change over 69. Then here you also remain with 20 because it didn't change over 69. Then here this minus 1 gives you 28, this minus 1 gives you 68, so you get 28 over 68. And yet it has not yet changed, so it is 20 over 68, and also this has not changed, so it is 20 over 68. Then for this one, this minus 1 gives you 19, and this minus 1 gives you 68, so you get 19 over 68. And here this one has already changed to 29, so it gives you 29 over 68. But this one has not yet changed, so it remains, it is still 20, so it is 20 over 68. Then for this one, this minus 1 is 19, this minus 1 is 68, so you get 19 over 68. Then white has changed because it was the one which was first picked, so it is 29 over 68. But this one has not yet been picked, so it is still 20 over 68. So that is a tree diagram which we shall use to get the required probability. So they want the probability that the first is white and the third is also white. So we have ignored these ones because they will not count in answering our question. So they want this and also third white. So they want that, this and that. That we shall come here and substitute those probabilities. So for this it is this, for this it is this, and for this it is this. So now when I use the calculator, we shall come up with 29 over 161 as the required probability. Now that has been method 1. What about method 2 of permutation and combination? Now like I told you, when the order is required, we use permutation. So in this case they want the order, so we shall use permutation. The 3 boxes are the 3 pickings, so first picking, second picking, third picking. Then you also have the options. Now here, picking the first one, you have 30 options. That's why here we see 30W. Then the third pick, this is done. Then the third one, you have 29. Now why is it 29? It is because you have already picked one from this 30W to put it in the first. Therefore, you are remaining with 29. We are remaining with 29 white. That is why in the third picking you have 29 options. Then the remaining ones will be for the second option. So here in the second picking, remember we have already picked one white here and one white here, so you are remaining with 28 white. That is why you have here 28W. But 20B is still intact, and also 20R is still intact. Therefore the permutation here it will be 30 permutation 1, and here it will be 68 permutation 1, because this is this plus this plus this. It is 68 permutation 1. And for the third one, it will be 29 permutation 1. Therefore, I'll come here and write that first white and third white means number of ways of picking first white and third white over sample space. So that means that it is 30 permutation 1, 68 permutation 1, and 29 permutation 1, as we saw in the previous slide. Then over the sample space will be 70, because we had 30 white, 20 blue, and 20 red. Therefore, total of this will be 70, but out of the 70 we need 3. That is why there is 70 permutation 3. So when I use a calculator, this gives me 30, this gives me 68, this gives me 29, and this gives me 328440. So numerator is this and denominator is this. Therefore, when we reduce, we'll come up with 29 over 161 as before. Then now we shall go to question 4. It says a bag contains 5 white, 3 red, and 2 green counters. 3 counters are drawn without replacement. What is the probability that Roman 1 there is no green counter, and Roman 2 there are 2 white counters and a green counter? So here, if you try using the method of a tree diagram, it will be so wide. So I'll leave it to you as homework, but for me I'll use the second approach of permutation and combination, which is a little shorter and brief. So probability of no green counter means that you can either pick 3 white, or 2 white and 1 red, or 1 white and 2 red, or 3 red, because they don't want any green over the sample space. So 3 white means that out of the 5 you need 3, and 2 white means out of the 5 you need 2, and 1 red means out of the 3 you need 1. Then here 1 white means out of the 5 you need 1, 2 red means out of the 3 you need 2, and 3 red means out of the 3 you need 3. So that's how the combinations are generated. Now 10 means when you add this 5 plus 3 plus 2 gives you 10. That is why out of the 10 you need 3. So when I use a calculator, this is this, this is this, this is this, this is that, this is this, and this is this. Therefore the denominator is also that. So when I simplify, I'll come up with 7 over 15. So if you try a tree diagram, it will also give you the same result. That is Roman 1. Roman 2 said there are 2 white and a green counter. So 2 white and a green counter. Still the order is not required. That's why we are using the method of combinations. So out of the 5 you need 2, out of the 2 you need 1, and total is 10, so out of the 10 you need 3, which gives you 1 over 6. So permutation, the method of permutation and combination is brief, but still you'll still get the same marks as the one who uses the tree diagram. So now we shall go to sampling without replacement given 2 bags. So previously it has been sampling without replacement from 1 bag, but now here we shall be given 2 bags. So if sampling without replacement consists of 2 bags, the best method is by using the probability tree diagram. So for 1 bag, the best method would be permutation, but when it comes to this, the best method is probability tree diagram. So question 1 says 2 boxes P and Q contain white and brown cards. P contains 6 white cards and 4 brown cards. Q contains 2 white cards and 3 brown cards. A box is selected at random and a card is selected. Find the probability that Roman 1, a brown card is selected, and Roman 2, box 2 is selected, given that the card is white. Note this word given. It means that there is a conditional probability somewhere. So let's start with Roman 1. So here we shall need to draw a tree diagram. So we have 2 boxes P and Q. So that means that probability of picking 1 box will be 1 over 2, and also this will be 1 over 2. Then from box P, probability of picking white is 6 over 10, therefore the complement is 4 over 10. From box Q, probability of picking white is 2 over 5, and complement is 3 over 5. Therefore you can now go and answer the questions. Question 1 says a brown card is selected. So brown, it means there is this option and also this option. Therefore P brown will be probability of box P intersection brown and plus probability of box Q intersection brown, which is this times this to give you this, and this times this to give you this. In the end you come up with a half as the required answer. What about Roman 2? For Roman 2, they want a probability that a box 2 is selected given that the card is white. So this is a probability and this white has already occurred. Therefore probability will be Q given white. So numerator is the intersection, denominator is what has already occurred. Now the intersection Q and white is that. Then white is the complement of brown, therefore that is why you see a 1 minus a half. Therefore in the end you will come up with 2 over 5, and that's the probability they wanted. So now we shall go to question 2. It says a box A contains 4 white and 2 red balls. Another box B contains 3 white and 3 red balls. A box is selected at random and 2 balls are picked one after another without replacement. Find the probability that the 2 balls picked are red. And Roman 2, given that 2 white balls are picked, what is the probability that they are from box B? So this has already occurred and they want this probability. So let's start with part A. So here you shall need a probability tree diagram. So now let's fill this tree diagram. Probability of picking box A will be 1 over 2 and also box B will be 1 over 2. Then if I pick white from box A, it will be 4 over 6 and the complement is 2 over 6. If I pick white from box B, it will be 3 over 6 and the complement will be 3 over 6. Then from box A, if I pick again white, it will be this reduces by 1 and also this reduces by 1 to give you 3 over 5. And the complement is 2 over 5. Then here this reduces by 1, this reduces by 1 to give you 1 over 5, and the complement is 4 over 5. Then here this reduces by 1 and this reduces by 1 to give you 2 over 5, and the complement is 3 over 5. Then here this reduces by 1, this reduces by 1 to give you 2 over 5, and the complement is 3 over 5. So with that we can go and answer the questions. So question 1 says, find the probability that the 2 balls picked are red. So 2 red means there is this red and this red, then also there is this red and red, which is this and that. Therefore, for this one there is this, which is here, and also for the other one there is this, which is here. Then simplify and use the calculator, will come up with 2 over 15. That is part A. What about part B? Part B says, given that 2 white balls are picked, what is the probability that they are from box B? So 2 white has already occurred, and they want the probability from box B. So 2 white from box B will be, first of all, probability of 2 white balls from box B is given by this. So there is this B, this, which is here, and gives you 1 over 10. But that's not all, so we shall also come here and so that 2 white balls is equal to this and that, which is this, and the end will come up with 3 over 10. So the probability of 2 white balls from box B, given 2 white has already been picked, is given by the intersection, which is still this from box B, over the what was already occurred, which is 2 white balls. Therefore this is that, and this is this, which gives you 1 over 3. So that is question 2. Now I shall go to question 3. It says 2 baskets A and B contain 8 red, 4 blue, and 5 red, 10 blue respectively. So A has 8 red and 4 blue, B has 5 red and 10 blue. A ball is randomly drawn from basket A and transferred into basket B. A ball is then randomly drawn from basket B. Find the probability that it will be red. So yes, still we shall need a tree diagram. So first of all, initially we have that, if you look at this, we have 8 red, 4 blue in basket A and 5 red, 10 blue in basket B, which is this. Therefore we shall come here and write that basket A we have 8 red and 4 blue. Now we are going to pick 1 red and put it here. If I pick red, it means that it is this option from here to this. So when I do that, it implies that how many were they? There were 8, so it will be 8 over 12. Now after that, you realize that in basket B we have 1, 2, 3, 4, 5, 6. We have 6 red and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 10 blue. Therefore, from there, I can pick red from here. So picking red means it will be 6 over 16 and the complement will be 10 over 16. That is the first action. Now what if I first pick blue? If I'm to first pick blue, it implies that it will be like that. Then I'll pick blue and put it there. If I put it there, it implies that now I'm going to have 1, 2, 3, 4, 5. It will be 5 red, and also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 11 blue. Therefore, picking red will be 5 over 16 and the complement will be 11 over 16. So now that you have filled the tree diagram, we can go and answer the question. So the question is, find the probability that it will be red. So probability that it will be red, there is this option and also this option. Therefore, if you come and write P red, it will be R1, R2, and also B1, R2. So R1, R2, we have this and this, which is here, and B1, R2, we have this and this, which is there. So now as a calculator, I'll come up with this as the required answer. Now we shall go to question 4. Question 4 says, one bag contains 5 red and 7 blue marbles. Another bag contains 6 red and 8 blue marbles. One marble is taken from the second bag and placed into the first. After thorough mixing, one marble is taken from the first and placed into the second. What is the probability, Roman 1, that there are 6 red marbles in the second bag? And Roman 2, the second bag contains an equal number of red and blue marbles. So still we shall need a tree diagram. So now let's start filling our tree diagram. So first of all, initially, this second bag has 6 red and 8 blue. So you come here and write, we shall write here 6 red and also 8 blue. When you do that, so if I want to pick red, it implies that it will be 6 over 14. That will be the probability. So that red will be put in the first bag. So this is what will have happened. So I have that first bag, second bag. So I'm going to pick red from the first bag and put it in the second bag. Sorry, from the second I put in the first. So when I do that, let me count how many I have in the first bag. So for red to be 1, 2. For red it will be 1, 2, 3, 4, 5, 6. So I'll come and write 6 red there. What about blue? So I have 1, 2, 3, 4, 5, 6, 7. So I'll come and write 7 blue. Now next is to pick again from the first bag, and I'm going to pick red and put it in the second bag. So when I do that, the probability will now be 6 over 13, because 6 is here and total is 13. And what has happened? This is what has happened. So I'll have picked red and put it in the second bag. Now how many do I have in the second bag? In the second bag I will have 1, 2, 3, 4, 5, 6. So I'll come and write 6R. Then blue 1, 2, 3, 4, 5, 6, 7, 8. So I'll come and write 8 blue. Okay, now let us go to this other option. For the second action, already the first one I had to first pick red, so let me first pick red from the second and put in the first. Now after that I am going to pick blue. Now to pick blue, the probability will be 7/13, and what has happened, this is what has happened. I'll pick blue and put in this second bag. So now let's count how many they are. So we have 1, 2, 3, 4, 5. So I come and write 5 red, then 1, 2, 3, 4, 5, 6, 7, 8, 9. So I come and write 9 blue. Okay. Then for this one, it implies that from the second bag I'm going to first pick blue. So when I pick blue, it means it will be 8/14. And what has happened, this is what has happened. So it means I picked a blue from the second and put it in the first. Therefore I have to count how many they are in the first. So 1, 2, 3, 4, 5. So there are 5 red. I'll come and write 5 red there. Then for blues, 1, 2, 3, 4, 5, 6, 7, 8. So I'll come and write 8 blue. So from here I can pick red. So if I pick red, it will be 5/13. And this is what has happened. So you pick red from the first and take in the second. So now let's count how many they are in the second. So 1, 2, 3, 4, 5, 6, 7. So I'll come and write 7R. What about blue? 1, 2, 3, 4, 5, 6, 7. So I'll come and write 7 blue. Okay, so that is this branch. What about this other one? So I'll first remove this. So here I first picked blue, so let me do that. Then after that I'm going to also pick blue and put in the second bag, so let me do that. So after that I have to count how many they are. So I'll come and say for red it's 1, 2, 3, 4, 5, 6. So I'll come and write 6 red. Then for blue it is 1, 2, 3, 4, 5, 6, 7, 8. So I'll come and write 8 blue. Okay, so now that you have filled the tree diagram, we can answer the questions. So Roman 1 says probably that there are 6 red marbles in the second bag. So 6 red, we have here 6, we have this 6 and also this 6. So the branch they want is this times this plus this times this. So let's do that in the next slide. So you come and substitute, then we can get the answer they want. So that is Roman 1. What about Roman 2? Roman 2, they want the probability that the second bag contains an equal number of red and blue marbles. So equal number, we only have this, which is this times this. So shall come here and write the equal number will be this times this, which gives you 24/91. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on resultant and relative motion. Remember, we have now finished probability and statistics. So next is now mechanics. So the first topic we shall deal with will be resultant and relative motion. So if you have not yet subscribed, please click on the subscribe button below this video so that I can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.